Unit 3 Chemistry, Chapter 9, Electrolysis. So this is the last topic in Unit 3. We're nearly halfway through, guys. And this last one where we are referring back a little bit to our redox. Okay, now remember your galvanic cells. Well, now we're looking at electrolysis, which is basically the opposite. So whereas a galvanic cell uses a redox reaction to produce electricity, okay, here we're going to use electricity to drive a redox reaction in the opposite way to the way they would occur spontaneously. So rather than going from chemical energy into electrical, we're going from electrical into chemical. Why would we want to do that? Well, we can use it to extract some pure elements, like some reactive metals. We can get them from compounds by doing this. We can also use it for plating things with a metal. So if you've got any gold or silver plated jewellery, that would have been done by electrolysis. And it's also very useful to recharge a cell. So every time you plug in your phone or your laptop, you are doing electrolysis, yeah? Because you are driving the reaction in the opposite way. And we have to have an input of energy. And in this case, the input of energy is not from heat, it's from the electrical energy. So electroplating is what we're going to look at first. We use it to coat an object with a thin layer of a metal. So anytime you've got a tin can or plated jewellery, that's been electroplated. For this setup, we're going to have one electrode that's the metal we want to plate with, which is this one. In this case, we're silver plating a fork. So the other electrode is our object that we're plating. Okay? We put them both in the same container this time. We're no separate containers for electrolysis, all in one. And in that we have a solution with the metal ions that are the same as the metal electrode. Okay? So here we have silver metal becoming a silver ion and electrons. So we are oxidizing our silver. Oxidation, of course, occurs at the anode. So this is our anode half reaction. Those silver ions go into solution. Other silver ions from solution will react at our cathode, where we'll have the reduction of silver to make silver metal. So there is no overall cell reaction. It cancels out. Okay. However, we will also see that the concentration of silver ions stays in the solution. But we still have two half reactions because stuff is still happening at each electrode. These electrons, which occur at the oxidation, are pulled away from the silver metal because it is attracted to the positive of a power source. And they are also repelled from the negative of a power source. So in this case, whilst our oxidation still occurs at our anode for electrolysis is now positive. And our cathode is now negative, but is still the site of reduction. It's only the signs that have changed. Okay, so at our anode, we have the metal being oxidized and ions going into solution. Okay, and those electrons are pulled towards the positive. At the cathode, we have electrons being pushed away from it, being repelled because it's a negative charge, and we have reduction of those metal ions to make the metal. We can do some calculations with electroplating. Michael Faraday, who you may have heard of, who's a great inventor, but he also investigated electroplating. And he found that there was a direct relationship between something which is called the charge and the amount of metal deposited. He found a straight line relationship. The charge, Q, is the current multiplied by the time in seconds. Okay? And it tells us essentially how many electrons are passing through the circuit in that time. No voltage in this calculation. The voltage has to be high enough to give enough energy for the reaction to occur, okay? Which we can work out using our electrochemical series. We can work out how much energy we need to put in, and it's got to be at least that. But it doesn't impact on how many electrons are flowing, because that's only basically the energy carried by each electron. Okay? So these are the straight line relationships we found. Okay? It's not the same relationship for all of them, but it's always a straight line. What we see is that if we've got something like silver, where we get a 1+ ion, or compare that to something like tin, where we get a 2+ ion, we need twice as much charge to plate the same amount of tin as we do silver. Chromium is 3+. Okay, we need 3 times as much charge to plate that amount. Okay. So what we found is that to deposit or to plate 1 mole of metal from an ion which has got a single positive charge, we need a charge of 96,500 coulombs. That number is known as a Faraday, and that value is in your data book. To deposit a mole of metal where we've got a 2+ ion, we need twice as much. To deposit a mole of metal where we've got a 3+ ion, we need 3 times as much. Okay, so that's true for all metals. So if we know the charge on the metal, we can work out how much charge we need how many coulombs we need in order to plate it, a certain mass, or if we know the amount of coulombs, we can work out what mass is going to be done, or if we know the mass and the coulombs, we could work out the charge. I know you're excited. Let's see how it's done. Okay. So if we wanted to calculate the mass of aluminium that can be electroplated by a current of 1000 amperes in 3.5 hours. That's big. We're thinking industrial scale here. First thing we always do is we write a balanced equation, or we don't really need to write it, we can just look in our electrochemical series. But we need the equation because we need to know what charge is on it. So we need to know also that ratio of metal to electrons. We start by finding the charge. Q equals IT, so our current is 1000 times 3.5 hours times 60 to turn it into minutes times another 60 to turn it into seconds. So you get 1.26 times 10 to the 7 coulombs. To find the mole of electrons, we then do the charge divided by that Faraday, that 96,500, which is a constant. So anytime you see F, you put in 96,500. Okay? And that's going to give us 130 moles of electrons. Now we do our stoichiometry. For each mole of metal, we need 3 moles of electrons. So we do 1 over got, so we're timesing by 1 over 3. So that's a third. Okay? So we find that we've got 43.5 moles of aluminium. Okay? From mole, we can of course find mass by multiplying by the molar mass of aluminium. So we'll find we get 1,057 grams, or once we simplify it down to 2 sig figs, because I've got 2 sig figs here, that's going to be 1.1 kilograms.